To analyse a thin film problem, all we want to do is find the points where we either have perfectly constructive interference or perfectly destructive. That means we have to find distances where the phase change is either 2 pi radians or a multiple of that for constructive, or pi radians or an odd number multiple of that for destructive interference. So let's look at the rules we need to follow. If a ray reflects off a boundary with a higher refractive index material, there will be a 180-degree phase shift. That means pi radians. If it reflects off a boundary with a lower refractive index, there is no phase change. We also have to consider the fact that wavelength is less in a higher refractive index compared to a vacuum, because the speed is less. That means we need to use the optical path length when light is moving through anything other than air. So let's start with a film of thickness T and refractive index N with air either side of it. A ray comes in from the top. Part of it is reflected from the top surface, and that is ray 1, and it has experienced a 180-degree phase shift. The ray that goes on into the film then will have part of it reflected off the lower surface. This can then come out at the top surface in ray 2. Now there is no phase shift at the reflection from the bottom surface, and there is no phase shift also when waves are transmitted. Now looking at ray 2, because it has made a return trip through the film, ray 2 has also gone a distance 2t through the film that had refractive index n. So that means it went through an extra optical path length of 2 times n times t. So when we're looking now at rays 1 and 2, and we want constructive interference between them, so we can say that the path length difference 2nt plus the 180-degree phase shift must be equal to a whole number of waves. So that is what we write as 2nt equals m plus a half times the wavelength. So that taking into account the extra distance that ray 2 has travelled and the 180-degree phase shift that ray 1 had. By the same logic, the condition for destructive interference is that 2nt equals an integer number of wavelengths. Because phase changes between rays depend on differences in optical path length and also on possible phase changes on reflection, we need to consider both of these when looking at any particular problem. Let's look at a case like this where we're going from a low refractive index material at the top to a medium refractive index in the middle, and then a higher refractive index at the bottom. So in this case, both reflected rays will have the same phase change on reflection because they're both bouncing off a boundary with a higher refractive index. So that means you can ignore that term, and the phase change between reflected rays now is just due to the difference in path length, which is 2n times the thickness T of that middle layer. And so in this case, where we're looking at constructive interference, we would say that 2nt equals m lambda. In this case, then we can know that for destructive interference, we would be saying that 2nt equals m plus a half times lambda.